All right. Hey, what's up, you guys? Welcome back to our second part of day two kinetics. And this is basically about second order reactions, and we'll also deal with half-life reactions. And we'll all kind of explain those when we get there, but they're a type of first order. So maybe this is a, I don't know, weird order to do things in. Okay. But yeah, here we go. Let's go ahead and get started. So things will be really similar. And we'll talk about integration first. So here's a second order reaction, right? And once again, right, your rate, here's your rate right here. Okay, here's another way to find your rate using the rate law. When we integrate that, don't ask me to explain that, please. When you integrate that, it gets rearranged so that it looks like this. Okay, and we get our good old y equals mx plus b equation, right? Here's our y-intercept, our slope, right? Our x variable, and not our y-intercept over here, our y variable, my bad, y variable here. Okay, our slope, our x variable here, and here's our y-intercept, which is our concentration divided into 1 at the time 0. Okay, so looks a little different, and this is only for second order reactions, right? So that means this: if you graph this second order reaction, you guys, okay, you get a I'll go magenta. We get a line with a positive slope, and it should be straight, right? So this looks a lot different, right? Here we have a positive slope as opposed to the first order reaction. We had a log of the concentration of A. We had a negative slope, right? So it looks a lot different, right? Only second order reactions will have a straight line with a positive slope using this equation. If it's not a second order reaction and we graph this, we get some kind of funky curved line or something, it's not a second order reaction, okay? Oh, and just like before, sorry, I'll move myself again. The rate constant is K, which is the slope. In this case, it's not the negative K, right? It is the K, right? Is the slope. And if you look back at our equation, which I'll show again here in just a second, you can see that. Okay. So when it comes down to this, you guys, it's all about straight lines and graphs. Okay. So we have a zeroth order reaction. I just like saying that. Okay, this is really a zero order reaction. And here, if we just graph the concentration of A versus time, we get just a straight negative slope, right? So the negative slope equals K, or the slope is negative K, right? The first order reaction, we get, if we graph the natural log of A, we get a straight line, okay? And the negative slope is equal to K, or the slope is negative K, right? All right, and then here, okay, if it's a second order reaction, if we graph 1 divided by the concentration of A, we get a positive slope. So these are all ways that we can kind of tell, looking at data, what order reaction we have, okay? It's all about the straight line, okay? And each of these has kind of a different rate law and a different equation associated with it. Okay, so let's talk about this. Let's look at rate laws, and we've got some data here, okay? And we find this, right? When we graph the natural log of the concentration of NO2, we get this funky curved line. So hey, it's not a first order reaction. However, when we look at the data of 1 divided by the concentration of NO2, we get a straight line. That means this must be a second order reaction. Super cool. Okay, so that means this, we can figure out the rate law now. And here's our rate law right here. Okay, our rate is equal to K times NO2 squared. Okay. Now, how can we do this? The rate constant. So here's how we do it, you guys. We take our integrated rate equation, right? Our integrated equation, and we just plug stuff in, okay? And I'll show you that here on the whiteboard. All right, that's right here. Okay, I just plug stuff in. I took my concentration at time, oh, not wrong side, concentration at time, at the second time there off the data table, right? And then I put my concentration at time 0 here, and then my time with the second piece of data that matches up with the 0.015, right? 100 or 1 times 10 to the second seconds. Okay, that goes there, and then I just solved for K. K ends up being 0.52, and because it's a second order reaction, I need molarity to the -1, seconds to the -1 as my units. It's just math, right? Okay, so here we go. Let's keep on rolling. Let's talk about half-life equations. By the way, the only difference between in the things that we've done, you guys, with first order and second order rates and rate constants and stuff is just the integrated rate law that we use, right? The integrated equation. Okay, so here's one with second order reactions, you guys. Okay, this is kind of like the one that we did at the beginning, dealing with that. And if we sketch a line, the experiment is repeated at a higher temperature. What would we expect? Well, I'll be honest. If it was at a higher temperature, I would expect my my rate law to have a higher slope here. That would be because AB would be decreasing at a faster rate. So therefore, my slope of my 1 divided by AB would be faster. Okay. Let's talk about half-life reactions. So if you've ever heard of half-life, you guys, you may have heard it associated with things like nuclear decay and things like that. Oh, I'm going to move my little square here a little bit. Oh, hello. Just a sec. Let me go back. Sorry. Anyway, this is time on the bottom. Sorry, that's off the screen, you guys. And basically, here's the deal. If we start with a certain concentration of A, after 1 half-life, half of it has gone. So let's say this. Let's say we start with, I don't know, 1 molar A, and my half-life is 5 minutes. Okay? My half-life is 5 minutes. Well, then that would be this. After 5 minutes, I would be down from 1 molar to 1/2 molar. Okay? And then after another 5 minutes, right, from here to here, this would be another 5 minutes. That would give me a quarter of the original A, which would be 0.25, right? After another 5 minutes, which would be 15 total, I'd be down to an eighth, or 0.125 molar. Okay, so that's the way that kind of works, you guys, with half-life. Now there's some equations and things we can use to do this. Okay, if we manipulate the integrated first order law equation to get the half-life equation, we get this right here. So my half-life is equal to 0.693 divided by the rate constant. Okay, makes things kind of easy, so we can figure out using our rate constant what the half-life of something is. So let's take a look at an example of that. All right, so it says find the half-life for the following reaction. All right, these are first order reactions, right? Okay, where we have one product that kind of one reactant that decays, right? So here's our natural log, here's our slope. They've given us some values there. So the first thing we're going to do is this. Okay, we need to find K. If we want to find the half-life, we need to know our rate constant. So we're going to find the slope of this line, and remember the slope of the line is the negative rate constant. So I did that on my whiteboard here, you guys. Whoop, let me get it in the right place. There we go. Okay, I did that. And I took the slope, the two y values, right? Up here, 4.93, and subtracted from that the negative 3.91. That gave me my kind of my rise or my decrease. And I divided that by the x value, which is 600. That gave me a slope of negative 0.0017. So since the slope is equal to negative k, then there's my k right there, is 0.0017. So remember, right, took the slope here, used the rise over run equation, just basic algebra, right? And then I use my half-life equation. This is found in your AP Chem packet, right? So 0.693 divided by k, my half-life for this reaction is 408 seconds. So that means this, right about here, about 408 seconds, I've passed one half-life. Whatever the original concentration of N2O5 was, it will now be half after 408 seconds. All right, one last question here. Okay, which of the following processes has the shorter half-life? Well, we've got our two rate constants here, and we know our rate equation, right? So that means this, you guys, process 1 has the shorter half-life because it has the greater rate constant, right? And if I divide this by a greater number, I will get a shorter or a smaller half-life. All right, I know that was kind of quick, you guys, but yeah, maybe not as quick as you thought it would be. But thanks for tuning in again. Hope you have a great day, and check out the practice assignment that I give you. Thanks a lot, you guys.